So hello everyone, I hope you're all doing very well. I checked a couple of days ago your essays, they all look alright. I'll start grading them during this weekend. Now the plan with the lectures for polymer physics or physical properties of polymers is today we will finish whatever we can in terms of revision, okay? With those slides that I'm providing you. I repeat, do not treat those slides as the only slides you need to revise for your final exam, okay? As I told you, these might be the main key points for the exam, but you still need to study the rest of the slides as well. So we will finish today with a revision, and then we have one final class on Tuesday, where I will bring you some revision questions, maybe some calculation questions, and also any questions you might have from either the revision lecture or from overall the whole year that might come up. Please let me know. Of course, I would expect that more questions might come up when you're revising for the final exam. That should be in 20 days or so. So since we will not have classes after that, feel free to contact me on my email or in the forum for clarification regarding any phenomena you don't understand or something that you would like to ask regarding the final exam. So on Tuesday, we talked about the polymer structure. We talked about the thermal transition, that is the glass transition, crystallization temperature, and melting temperature. And today, let's get started with talking about polymer processing. You remember polymer processing, we spent quite a bit of time in discussing how do we generally process polymers, and what are essentially the shapes that we can produce with different polymer processing techniques. The truth is that for the polymer processing section, I don't want you to remember exactly parts, let's say, of the technique. So I don't want you to be able to describe, let's say, the different parts of an extruder or an injection molder, but generally have an idea of how these processes operate, very rough idea. But the most important is that I want you to be able to identify different types of polymers and different techniques in order to process polymers for a specific application, okay? So let me write it down. I want you to be able to identify polymers Okay, so if you understand that, then we have achieved what is the target for the polymer processing chapter, essentially, is you being able to see a certain polymeric product or application and identifying approximately what kind of polymer is used within this application. Simple applications, okay? And how is this shape or how is this polymer processed in order to be used in such an application, okay? We said that the majority of polymer processing techniques is, not the majority, the main polymer processing techniques are extrusion and injection molding, and both of them operate at temperatures higher than the melting point. So for semi-crystalline polymers, okay, for polymers which have a melting point, And the process of extrusion is relatively simple. What we do is feed our materials here. We have the turning screws and the motor here. And once the polymer goes in the extruder, it is melted, okay? And it travels throughout the extruder and it comes out from the shaping dies. The shaping dies can have different types of shapes, but generally, by extrusion, we can only produce very simple shapes. Only produce Does anyone remember what is the main problem with the extrusion that prevent us from extruding, let's say, complicated shapes? What is the problem with a polymer that comes out from the melt? What is the problem here with this technique? Can anyone tell me in WCOM? WCOM, yeah. I finally learned it last class before finishing. Very well. I have some questions in the polymer group, which are indeed correct. Materials people? Anyone? Yeah. The cracking of the melt can be a problem indeed. It is less usual than die swell phenomenon. Okay. Give me a second. Yeah. 2 people in polymer. So we have the die swell phenomenon. Sorry. Which leads to low dimensional stability. Since as the polymer comes out from the die, it swells, okay? That is as a result of the melt elasticity of polymers. So the dimensional stability of the polymers when extruded, especially semi-crystalline polymers, is relatively low, and that is why we cannot extrude very complicated shapes rather than some simple tubes and pipes or sheets and films, okay? The melt crack that someone mentioned is indeed a significant problem. It is usually caused by tuning the settings of the extrusion rather than the polymer characteristics itself. So the melt crack can come as a result of a lot of pressure that is developed throughout the extruder, or very high speed of the turning screws, okay? And that leads to significant aggregation of pressure throughout the extruder and melt crack, as you said. Now, along the extruder, we can add another feeding line. So let's say we can either feed the polymer with something else here, or we can have another feeder, let's say here. Where we have, I don't know, different substances, and we can use an extruder for different types of production of different types of materials, such as composites, such as plasticizer. Can anyone tell me what are the properties, the 2 mechanical properties that are generally increased adding a plasticizer within a polymer? has a modulus of 1 to 2 gigapascals. Okay, some correct answers in the polymers group. Materials. Indeed. So if we add plasticizer within a relatively stiff polymer, what do? We increase ductility. And as a result, we increase the toughness as well. Okay? So PVC without the plasticizer can have a modulus of 1 to 2 gigapascals, while PVC with a plasticizer can have a modulus of around, let's say, I don't know, 35 to 50 megapascals. So that behaves as, it becomes as soft as an elastomer. So you can realize we have one order of magnitude, almost one order of magnitude, no, 2 orders of magnitude difference in stiffness, which is very, very significant. Okay. Now we can also add a second polymer in order to create polymer blends. We can add pigment in order to give a polymer a certain color that we want for a certain application, and also we can do recycling. How do we do recycling or recompounding? We said that the advantage for semi-crystalline polymers, okay? We said that the advantage of semi-crystalline polymers and polymers in general is that if we have a failure of the polymer, we can remelt it and reprocess it because we can recrystallize our material as many times as we want. Can anyone tell me which are the materials that cannot be recycled by recompounding or reprocessing? Which family of polymers cannot be essentially reprocessed as a result of their structure? Have an answer in materials. Anyone else in materials besides Gigi? It seems that he's pulling all the weight for you. There you are, Dorian, come on. Indeed, some correct answers in materials group, polymers. So which are the materials, the family of polymers which cannot be reprocessed after failure? Anyone from the polymers group? Very well. Indeed, thermosets cannot be reprocessed because they have these chemical crosslinks which essentially prevent the materials from melting and recrystallizing and so on. So thermosets cannot be recycled, only semi-crystalline polymers can do so. Now, seat extrusion is one of is an important technique that is used to fabricate thick seats. Okay, so at the end of the die, we have this 3-roll stack, which we essentially control the thickness of our material by controlling the distance between the stacks and the force. Essentially, that is the force that is applied to the polymer that travels through the stacks. And then by cooling it, we have a winder here and we collect the thick polymer seats. Okay. Now, co-extrusion is another technique that is used to create multiple layer films. Co-extrusion is essentially a technique where 2 or more extruders are connected in series, so they extrude in the same region, in the same area, and then the polymer is collected from this same area, and it forms this multiple layer structure that can help us achieve multiple functionalities. Okay, You remember we mentioned about co-extrusion for the production of films for food packaging, okay? Because over there we certainly need protection from the outside environment, but also we need protection from gases, we need protection from moisture, so we need polymers that are that cannot be easily penetrated by moisture or gas, okay? And one characteristic polymer that behaves very well in these conditions is EVOH, which has very low permeability. Gas or moisture. It's ethyl vinyl hydroxide, something like that. EVOH, ethyl vinyl something. So blow and fill extrusion is another technique which essentially utilizes an extruder, and then at the end of the extruder, at the die, we have this airing. So we apply a lot of pressure at the melt of the polymer that is not melt, the polymer that is between crystalline state and melt state. And because we apply that air, we create this air bubble here, and we use blow and fill extrusion to produce thin films, such as thin plastic bags and so on. Okay. Now, this graph is important because essentially it links the thickness of a polymer with the melt flow index. Okay. And you remember what we said, that for thick films, and you can see here, you can see this data here, for thick films, we generally need low melt flow index. That means, you remember again, we said melt flow index is proportional to the inverse of viscosity. So that leads to high viscosity. And generally, we have high viscosity when we have high molecular weight polymer. Okay, so in order to create thick polymer films, what do we need? We generally need materials with high molecular weight in order to achieve high viscosity. So also for thin films, we have low viscosity, low molecular weight, and high melt flow index. Okay. Rubber compounding is another technique. It is mostly used to process rubbers or elastomers. And as we said, this is very simple technique. We put the rubber in here, and these two rolls counter-rotate, and we process the rubber. What is the process essentially that we need to follow in order to make a rubber useful? Can anyone remember how is it called? The technique that, not the technique, the process that we generally follow every time that we process a rubber material? What do we do here? What do we do after we process the rubber within 2-roll mill? Does anyone remember the process? How is it called? Anyone? No, it's not water bath. Indeed, we need to perform vulcanization, as Joan said, vulcanization or curing. is the same, okay? So what we do is here, the material, the rubber is uncured. So with the rubber in there, we also add the curing agents, okay? So we add and then once we get these seeds of rubber, we need to do a hot pressing process in order to activate the curing agents and enable cross-linking of the rubber. Okay, so here we do not only add the rubber materials, but we add the curing agents, the accelerators, any reinforcements that we want to add, such as carbon black or clays or silica and so on. Okay, calendaring is a similar technique to rubber, but to roll mill, but it has many roles, and generally it can operate under elevated temperatures. So it is a process of fabricating films with different types of polymers, such as thermoplastics and amorphous polymers and so on. Extrusion molding is a technique that is very commonly used in order to fabricate bottles. And at the end of the extruder, we have the formation of these partisans. And then we have a mold that closes, and we again blow air in there in order to fabricate those bottles or whatever the shape of the mold is. Extrusion molding takes place at temperatures between the glass transition temperature and the melting point. Okay, because we want here the material to be soft, that is higher than the glass transition temperature, but we don't want it to be liquid. Okay, we want to have at least a certain amount of stiffness in order to attach the polymer to the walls of the mold once compressed air is used. Okay. And as I told you, injection molding is the second most common polymer processing techniques. You can imagine, you can consider injection molding similar to a vaccine. Now that in topic, okay. Now a lot of people are talking about vaccines. So injection molding essentially operates in the same way. We inject something, which is where something is the molten polymer. So we inject molten polymer in complex or simple as well molds or mold. I never learned how to write it. What is the correct way of writing molds? I think the one is UK English and the other is American English. Anyway, how does an injection molder operate? As I told you, we feed in the polymer here. The polymer is molten over in this region here within the barrel, and by the screws, the polymer, it travels at the end of the injection molder, and then these screws go back, and then they go forth, injecting the polymer with force within these mold plates, okay? And the mold plates essentially consist from a platen that is stable and one that is moving. Okay, and then after it cools down here, or solidified, let's say, or crystallized, then the movable platen opens and we take the polymer from there. Injection molding is a very fast process, okay, and that is why industry likes it so much, because within a very short amount of time we can produce a large number of materials. So an injection molding cycle can take from 35 seconds in general. But an injection molding cycle looks like that. Firstly, we close the mold, the polymer melts and fills the mold. Then we keep the polymer at constant pressure within the mold in order to stabilize the polymer within the mold. Okay, that takes place at constant pressure. And as you can see, the part of the cooling is the most time consuming, okay? And finally, we inject the part. So the whole process takes place at a time scale of a few seconds. Now, there is this processing window of injection molding. And in order to fabricate a good-looking polymer with a structure that is the way we imagined, and the properties of the polymer will be the way they should, we need to stay within this processing window. This is called the processing window. If we move outside this processing window in terms of temperature or pressure, we will have problems, okay? If we have extra pressure, or if we have additional material, then we can have flash. Flash is the phenomenon where excess material comes as part of the produced material. So afterwards, we need to cut the excess material and so on. So flash is essentially associated with extra material. Now, if we use very high temperatures, we are afraid that we can induce thermal degradation. So the polymer is burned essentially. While if we use very low temperatures, we do not melt enough the polymer, and then we have this phenomenon that is called fish eyes, okay? Where essentially the polymer melts are not completely molten, so some polymer is molten and some is not, so the appearance of the material is not very good. And finally, we have a short shot at low pressures, where the material is not enough usually. That can also happen because of very low pressures, as you can see in this region. Okay. And finally, this is the graph that we have seen 1,000 times. So the reason we use this graph at this stage is that for different states of polymer, we use different types of processes. And let's start with the simple ones. Here, for a semi-crystalline polymer, we have the melting point, okay? So these techniques all take place at temperatures higher than the melting point, okay? Also, the other very simple case is here, where we have the glassy state, where essentially we know that the chains are frozen. In this case, we use the glassy state of the polymer, or essentially we cool down a polymer to its glassy state in order to demold, to take the polymer out of the mold or use it, okay? And also for temperatures, for the rubbery region, where the temperature is between the glass transition and the melting point, we have processes that take place such as vacuum forming and bottle blowing, okay? Where essentially we need a certain amount of flexibility from the polymer. Okay? And that's pretty much it from polymer processing. Let's go now to another section that we discussed during the semester, which is the rubber and fluid phase, or some characteristic of elastomers and some characteristics of the polymers when they are in the fluid phase. And more generally, this has to do with their viscosity, mostly. So we said in order to characterize a polymer as an elastomeric, the polymer needs to satisfy three main conditions. Firstly, the polymer must be above its glass transition temperature at room temperature. Or in a temperature that we experience the polymer. It can be slightly higher, I don't know, in summer in Sian, it can go easily above 30 degrees. So generally polymers must be in their rubbery state above its glass transition temperature. The polymer must have a very low degree of crystallinity, obviously. In elastomers, we don't have ordered regions of polymers, of macromolecular chains. There's no order. While also we need a small amount of cross-links between chains, okay? But cross-linking must definitely take place in order to make an elastomer useful, okay? We always need to essentially follow the process of cross-linking in order to bring usability onto an uncured elastomer. Then the curing process is a bit unclear on how it takes place, but that won't bother us too much. Cross-linking usually takes place by two activators. Can anyone remember what are the two external forces that we can use in order to activate the cross-linking? We had mentioned two things that we need after we mix the polymer with a cross-linker in order to activate the cross-linking agent. What are these? Anyone have an answer in polymer group? Indeed, heating is one process. The second, what else can we do? Indeed, Monday is correct, and blue is correct as well. So after we mix an elastomer with a cross-linking agent, we need to activate a cross-linking agent, and the cross-linking agent is usually activated by temperature and usually some pressure. That takes place in a hot press. Hot press essentially is this machine where we compact a sheet of polymer. Let's say this is a polymer. We compact it between two plates and we heat it up in there under constant pressure. Okay, so we apply a temperature and some pressure, or we apply UV radiation. You remember that we were talking about how a rubber band can suffer if it's left for too long under heat, because the combination of both increased temperature and UV light can lead to a very high degree of cross-linking points. And as we said, in order for a polymer to show an elastomer to show elastomeric properties, we need the amount of crosslinks to be low. Okay, if it's high, then the rubber band snaps very fast. So yes, here we have the glassy state below the glass transition temperature, where the modulus is determined by secondary interactions. Well, above the glass transition temperature at the rubbery state, we have said that there is enough thermal energy in order to change the conformations of the change. And because we can change the chain conformation, we can have a rotation of the chains around their bonds. So we can essentially start to disentangle our chains towards the end of the rubbery plateau. It's called the rubbery. And we have talked already how to prolong this rubbery plateau if we want, is essentially by creating more entanglements between the chains or by adding more crosslinks. But of course, we need to be careful on the amount of cross-linking that we will do, because more cross-linking, as we said, will decrease the elastomeric character of a polymer, and it will not be able to elongate at long strains, large strains. Okay, and this is an interesting phenomenon that takes place in elastomers. If we check the stress to strain for an elastomer, the curve looks like that. Okay, there is a deviation from theory, and that is because we have what is called strain-induced crystallization. Because in elastomers, the chains are able to elongate a lot, as they have a low amount of crosslinks and a lot of free volume in there. Because the chains can elongate a lot, at a certain point, the chains come close to each other, and then intermolecular interactions take place between the chains, and we have the formation of crystalline regions. Okay, formation of crystallites at large strains. Okay, and because these crystallites are able to slow down, deviate, and even stop crack growth, the actual curve at the large strains can show a deviation from theory, where essentially the stress increases. Okay, and that is the equation of the stress for elastomers. Also, we had this brief discussion yesterday on how to prolong, if we want, the glassy area, or generally how do we increase the glass transition temperature. Okay, and that can take place with increasing amount of cross-linking or increasing network density as well. As you can see, the increased cross-linking can lead to an increase of the modulus of the rubbery plateau. Yeah, rubbery plateau modulus increases with cross-link density. Also, the amount of entanglements, we said that it affects significantly the rubbery plateau, because when we have more entanglements, we want to have the chains disentangling in order to slip against each other. Of course, we don't have melting in this case because we have a cross-linked material, but longer chains, as we can understand, have more entanglements, and as a result, we need more significant thermal energy in order to make the chains disentangle between themselves. Of course, I repeat, we will not have, in this case, the melting part of the module versus temperature change. And the longer chains, as we said, are essentially represented by the Z average molar mass. Yeah, it's called here. This is the longest chain. Higher averages as MZ govern the rubber to fluid transition. Thermodynamically, what happens when we're stretching and unstretching release the stretch or the strain from a rubber is essentially the phenomenon that's called entropy spring, where the polymer, as we said, the elastomers, as we said, they want to be under maximum entropy. So what we do when we have unloaded chains, when we stretch a polymer, we reduce the amount of conformations. So in this case, we reduce the amount of entropy. The polymer does not like that, and it tries to recover its original shape. And in elastomers, this can be done by this entropy spring phenomenon. Okay. Number of chain conformation decreases, as we said, the entropy decreases, but the polymers generally like to have maximum entropy, and that leads to recovery of the original shape for elastomers. Let's take a 10-minute break now, and then we will have start discussing about viscosity or the melt state of a polymer. So I'll see you in 10 minutes. Okay, so let's get started with the second part of today's course, and let's resume our revision by looking into viscosity. And viscosity, as we said, it's very important for polymers because essentially it dictates how we process material, and can give us significant information regarding curing characteristics and so on. Okay, so we talked about the units of viscosity, which are Newton times second over square meter, or pascals over seconds. Does anyone remember the third type of unit for the viscosity? There is a third kind of unit. Not sure if I have mentioned it. I remember. The third kind of unit is called poise, okay, or P, and it's equal to 0.1 Pascal over second. Viscosity is generally defined as the ratio of shear stress over shear rate, and essentially it can be represented if we have a polymer between these two plates. I try to move the upper plate in order to observe shear. Okay, we obtain this force that we need to move the upper plate, and once it starts moving, we move it at a constant speed. Okay, so the shear stress is given by the shear force over the area of the upper plate, and the shear rate is given by the ratio of the speed over the distance between the plates. Okay, let me, because I don't like this graph over here, let me remind you of the different behavior of materials in terms of shear stress and shear rate. So there are four main types of materials in terms of shear rate, which is gamma, and shear stress, which is T, tough, big tough. So we have four main types of materials. Firstly, we have the simplest case, which has Newtonian behavior. And as you can see, the shear stress is proportional to the shear rate for Newtonian materials. Then, the most common case for polymers is pseudoplastic. Okay, it's most common. Okay, where essentially the with application of shear stress of shear rate, the shear stress increases very fast and then starts saturating at higher rates. Okay, and also we have dilatant behavior, where essentially we have this phenomenon that is called shear thickening. With the application of shear stress, the shear rate increases not very fast in the beginning, and then it starts increasing exponentially. And finally, we have these materials that are called Bingham plastics. And essentially, as you can see in this case, shear needs to be applied to induce flow. And we said that being plastics are materials, let's say, such as ketchup or toothpaste or your shampoo and so on, where you need to move them to give them a certain amount of shear in order to induce flow in them. Okay, let's go back to the slides. Now, this is an important graph which shows us how the viscosity is affected by the molecular weight. Okay, and we said that below what is very critical, the molar mass between entanglements, the viscosity is proportional to the molecular weight, while above the molecular weight between entanglements, the viscosity increases. The viscosity is proportional to the molecular weight to the power of 3.4. Okay, so doubling the molecular weight in this region can get a 10-fold increase in viscosity. So that is 2 to the power of 3.4, okay? Approximately 10. Okay, so you can see how pronouncedly the molecular weight can affect the viscosity when the molecular weight is above ME, okay? Now, as I told you, there are two main behaviors of polymers. It's pseudoplastic, which is essentially associated with shear thinning. And in shear thinning, we have a decrease of the viscosity with increasing shear rate, okay? And that is the most common case for polymers. So what happens in this case? That we have three main regions where we divide this viscosity over shear rate graph. The first region at low shear rates, there is not enough energy, that is in this case mechanical energy, in order to disentangle the chains or start disentangling the chains. So the viscosity in this case is constant. And then obviously with increasing shear rate, we provide enough mechanical energy, I repeat, so we have a mechanical energy to start aligning the chains next to each other, okay? From a highly entangled situation, we start aligning them by applying shear, and that leads to a very significant reduction of viscosity. Okay, and finally, when the chains are highly aligned at high shear rates, then of course, given that the chains are aligned and we have high rates, the viscosity remains constant and very low, okay? The shear thinning behavior is very important in several polymer processing techniques, such as injection molding, because injection molding, as we said, it involves very high shear rates. So we have the polymer melt here, and then we inject it very high onto the mold, okay? So if we have shear thinning behavior, what happens is that because we apply very high shear rates, the viscosity drops. And because the viscosity drops, it's generally easier for us to process our material, okay? And that is why shear thinning is beneficial for major polymer processing techniques, such as injection molding and extrusion. Okay, you get it. For the case of the injection molding is a matter of how fast we inject our polymer, so how fast we apply the shear rate by injection, while in the case of extrusion is how fast we induce a turning of the screws. So we apply higher shear by moving the polymer faster within the barrel of the extruder. And in this case, we have again the viscosity drop because of the high shear rates as a result of the induced increased RPM of the screws. Now, the inverse of shear thinning is shear thickening. Okay, and it's a bit uncommon, but it's generally very interesting because in shear thickening behavior, what happens is that the fluid's viscosity increases dramatically with increasing shear stress. Okay, so in this case we have the viscosity versus shear rate. Okay, it's a constant -1. In this case we have a behavior that looks like that. Okay. And in this case, we have when we're moving, let's say, the boundary plate, the upper plate here, in order to induce shear, we don't have this arrangement of the chain. We have a further disorder. Okay, it's like we're dispersing further the chains in there, and we have this thickening behavior afterwards. And a very characteristic shear thickening combination is cornstarch. I will write it down here. You remember we saw this example where people were mixing cornstarch and water, and they were creating this shear thickening material. Now, as I told you, viscosity is very important in terms of polymer processing techniques. And yeah, we already discussed about injection molding, which which involves high shear rate. So shear thinning behavior is highly beneficial because we either use lower injection pressures and we can generally process our materials much easier. While in the case of shear thickening materials, we generally benefit from shear thickening behavior in a process that's called rotational molding, where in rotational molding, what we do is we melt the polymer. So we melt the polymer here, and then we start moving, let's say not moving, apply shear from multiple directions in order to induce the polymer melt to touch the walls of the mold. And in this case, shear thickening is interesting because we want the polymer to thicken as it touches the walls. So initially, after it touches the walls, it becomes stable at the walls with increasing shear, and we have a stable polymer product. Stable at the end. Okay. Now, let's move on and let's go to blends and copolymers, which is another chapter that we discussed throughout the semester. And generally, as we said, blending is a process where we combine two polymers without too much sophistication or too much precise chemistry, while in the case of copolymerization, we apply very precise chemical processes during polymerization in order to control the structure of these polymers. And that is why, because we provide very high degree of precision during polymerization, that is why copolymers can show very interesting characteristics such as self-assembly, of the structures down to nanometer scale. Okay. The problem with blending is that most polymers are immiscible. Okay, so most polymers don't like each other unless they are from the same family of materials, such as I told you, low density polyethylene with high density polyethylene. Okay, so then we're talking about the same family of materials, and the two criteria for miscibility is firstly the negative Gibbs free energy of the blend, and also the derivative of the second derivative of the Gibbs free energy. The Gibbs free energy of the blend needs to be negative, and the second derivative of the Gibbs free energy over the composition of the blend needs to be positive. Okay? And we have generally four main methods for preparation of polymer blends: melt mixing and fine powder mixing, which this one and this one take place by extrusion. Or injection molding sometimes. Solution blending, we said that we dissolve the two polymers within a common solvent, and then we mix them while they're dissolved within the solvent. And latex mixing is commonly used for elastomeric materials. So we create these water emulsions in order to mix them, to mix two elastomers in a kind of watery form. Okay. Now, the Fluorescence equation. This is an equation that I ask you to remember, and this is the phase behavior or phase diagram of polymer blend. Okay. A phase diagram in general is a diagram of temperature versus composition, and it shows different regions of miscibility, okay, where two materials can be combined or they cannot be combined. Now, in a phase diagram for a polymer blend, we have the two-phase region, where essentially these are the regions of immiscibility. And also we have a single-phase region where we have miscibility. The two-phase region and the single-phase region are separated by these curves that are called binodals. Okay, binodals are the curves that separate single-phase with two-phase, And there is a metal stable region here, where these curves are separated by this dotted line here that is called spinodal curves. Okay. Obviously, if you remember the Fluorescence Equation, this one, then you can fabricate a phase diagram for a polymer blend, and that can be done by obtaining the condition for phase separation, where the second derivative of the Gibbs free energy is equal over composition is equal to 0. Okay, and that leads to the fabrication of the theoretical spinodal points, and by fabricating the spinodal points, we obtain these curves here, and also we can obtain a critical composition above which we have a separation of single phase and two phase region within a phase diagram. Okay. So for the critical composition, we take the third power of the Gibbs free energy, the third derivative of the Gibbs free energy, and it leads to the critical value of the Fluorescence interaction parameter as well. Now, how do we detect generally miscibility in a lab environment? This is generally done by looking at the glass transition of the blend and compare it with the glass transition of the homopolymers. Okay, homopolymers are the two polymers that are essentially combined in order to create the blends. By using this, I think it's called the Fox equation. Not fully sure though. Let me refrain from writing that. For completely miscible polymers, we have this very simple equation, which gives us an approximation of the glass transition of the blend, where W1 and W2 are the contents, the weight percent of each polymer, and TG1 and TG2 are their respective glass transitions. Okay, so if the blends are completely miscible, we have two glass transitions. If the blends are miscible, of 1 TG. Okay. Now there is a number of methods that we can use in order to compatibilize polymer blends. The majority of them have to do with the fabrication or the creation of graft or block copolymers, which are targeting in stabilization of the interface between the two polymers. Okay, so what we do is either we do in situ polymerization, which, as I told you, leads to the formation of a graft or block copolymer. Reactive compatibilization is essentially by introducing a third polymer that is miscible with one phase and reacting with the other. Again, that leads to the formation of a graft copolymer. Reactive extrusion, which is very similar, again leads to graft copolymers. Okay, and also another nice method is by adding a third. Ternary is a third polymeric material which has good interfacial adhesion with both phases and concentrates in the interfacial region. And essentially by saying addition, by saying addition of a block copolymer here. Essentially, this is a process which is very similar to the other processes we just discussed, where the copolymer is concentrated onto the boundary between the two faces, and that provides the lowest free energy to the system. Okay. So if we have the two polymers, the purple one and the green one, we have a copolymer that block A is compatible with the purple polymer, and block B is compatible with the green polymer, and that helps them. That helps with compatibilization of this polymer blend. Yeah, the different types of copolymers, it's fine. These are very simple. And also, as we said, the interesting part with the copolymers is that we can use a very precise chemistry to fabricate them. And because of that, the copolymers are able to self-assembly down to nanometers through phase separation, okay? So depending on the three parameters which can control the phase structure, those are the three parameters. The simplest one, the composition of the copolymer, X, the degree of polymerization, and he, the Florey-Huggins interaction parameter, which is given by this simple equation, where A and B are constants. So again, it depends only on the temperature. So by controlling these three parameters, we can control the nanoscale features that we induce onto our copolymer, okay? And as you can see, by controlling the nanoscale features, we can fabricate different unique structures in the nanoscale, such as spheres, cylinders, these back-contiguous structures, which are very difficult to draw and very difficult to fabricate as well, because they have the narrowest composition range. Okay, and finally the lamellar structure, where we have alternating layers of the two polymers. Here we have a decreasing temperature with increasing product of X times he, because he, as we said, is proportional to the inverse of the temperature. That's why we have decreasing temperature with increasing he over he. And these are generally the composition of the minority polymer and the shapes that we can get. These are nanometer type of structures, okay? And you can see that for spheres, we have volume fractions in the order from 0 to 20%, cylinders 21 to 33, this complex structure from 34 to 37, and 38 to 50. Okay. And now let's go to the final chapter. We will very briefly talk about, which is the mechanical properties. We will not be revising, even though I have provided you slides for the viscoelasticity. We will not be revising that. We just did we do it? No. We had a revision, not revision, we had this class for viscoelasticity last week, so these are relatively fresh to you. So in the next, how much time we have? 15 minutes. Let's revise a bit some of the contents of the mechanical properties. And these are some characteristic stress-strain curves for different types of polymers, okay? Now, as I told you, this is not a great graph, because elastomers can certainly elongate more than semi-crystalline polymers. Okay, and sometimes they can even obtain higher stress and so on. So let's use this graph only for the modulus. And can anyone remember how do we obtain the modulus from a stress strain curve? How do we obtain the modulus from a stress strain curve for different types of polymers? It doesn't have to do a specific one. Anyone remember? I have one answer in the polymers group. I want a couple more. Come on. I have one answer in materials group. Indeed, as Zhu said, is the slope in the elastic region of the stress strain curve. Okay. Oh, I'm an idiot. It says it here. Great. So yeah, the initial slope of the stress strain curve gives the modulus. Sorry about that. So this part here can give us the modulus. You can see that we have already talked that polymers are a huge family of materials, right? And because they are so big family of materials, they can show very, very different characteristics. And the modulus is one of the properties that can vary so much across different types of polymers, okay? So for elastomers, their modulus is generally in the order of a few megapascals or tens of megapascals, okay? And that makes them very soft. Now, semi-crystalline polymers, we said, that they have a combination of amorphous and crystalline regions. And as a result, they have higher stiffness compared to elastomers because the crystalline regions can give more elasticity to our polymer. So in this case, we have moduli in the order of a few gigapascals. Glassy polymers also is in the order of gigapascals, few gigapascals, or let's say also higher than 0.5 gigapascal. Glassy polymers are certainly within the order of gigapascals, while polymer fibers, where essentially the chains are oriented the orientation of the chains, as we said, brings a very high ultimate tensile strength and a very high modulus to our polymers. And when the chains are oriented parallel to the pulling axis, we can have moduli very high that are in the order of hundreds of gigapascals, okay? While if they are oriented perpendicular to the pulling direction, so we're pulling in this direction and the fibers are oriented like that, then we don't have a significant effect of the orientation because they are oriented in the wrong direction, okay? Now, for elastomers, we already talked about their behavior in the initial state of the stress strain curve. The chains are lightly cross-linked, and they're able to elongate a lot, but the slope of the stress strain curve is very low because they have enhanced softness. We said that for elastomers, we generally can obtain their modulus in different areas of the stress strain curve because they can elongate so much. Okay? Sometimes we get the modulus at, let's say, 50% strain, or we can get the modulus at 150% strain, or so, and so on. Okay, that is what, because elastomers can elongate a lot. For the other types of materials, such as thermoplastics and so on, we only look at the elastic part of the stress strain curve. Indeed, the deformation is reversible for elastomers, and we see at the last part of the stress strain curve, we have this significant increase in the ultimate tensile strength because of orientation of the change along the pulling direction. Okay, and we have strain now for thermosets. The situation is slightly more clear. Thermosets have a high stiffness, they generally show high strength, and they show low elongation. They are brittle. Okay, and that is because they are highly cross-linked, and the cross-links do not allow the change to move along with the orientation or with the application of the strain. Okay, and that leads to an early failure, brittle failure. And finally, semi-crystalline polymers are the most interesting parts, the most interesting materials in terms of the stress strain behavior. Okay, because amorphous regions and crystalline regions deform differently. Okay, in the elastic part of the stress strain curve for a semi-crystalline polymer, only the amorphous regions elongate. Okay, so in the elastic region, the crystalline parts are not affected by the application of strain. Only the amorphous chains are starting to orient along the direction of strain. And then when we reach the yield point, we have plastic deformation. Okay, so deformation after the yield point is not reversible, it is permanent. And in this case, usually what happens that we have a sliding of the crystalline regions. Okay, so after the crystalline and the amorphous regions kind of align at the yield, then we have a sliding of the crystalline regions after the yield. So that drops a bit the stress, but then again we have an reinitiation of the orientation of the chains, and that is why we have this what is called strain hardening phenomenon, because the crystalline regions, even though they are smaller in size in this case, they again start to orient themselves along the pulling direction, and that leads to an increase of ultimate tensile strength. Okay, let me take it out. Ultimate tensile strength. Okay. Now, in order to create the fibers, we do this process that's called drawing, okay? And drawing can be hot or cold, but what we do essentially is we're drawing our materials in order to orient the change. And with the higher draw ratio, as you can see here for polypropylene, where draw ratio is the length of the neck sample over the length of the original sample, we said that semi-crystalline polymers they form these necks, and these necks are highly oriented chains. Okay, and because of the very high orientation, if we test the mechanical properties of the necked region or the highly oriented region, that shows a very pronounced increase in both strength and modulus. Okay. Also, there are some effects that some parameters that can affect significantly the measurements of our mechanical properties are both the temperature and the strain rate, how fast essentially we're pulling and at what temperature we're pulling. At increased temperature, as you can understand, the chains have a higher mobility, and because of that high mobility, they're able to slip quickly against each other, and that softens the material. They are closer to their rubbery state, and that leads to a reduction of the modulus, a reduction of the tensile strength, and an increase of the strain at break, as you can see for PMMA. Now, for amorphous materials, or for glassy polymers, which are the most complex ones in terms of deformation, and we cannot pretty much predict how they will deform. They deform by two main methods: necking, which we already discussed, where we have this growth of this neck here, or crazing, where crazing, the stress is localized at some parts and leads to brittle fracture. Okay, so a crazing polymer, a crazing elastomer will look like a crazing glassy polymer, which have a stress strain curve that looks like that, while a necking amorphous polymer can have a stress strain that looks like that. Okay, let me use blue for. Okay. Crazing takes place by essentially forming a localized plastic zone, and then this grows by opening up like a hole. You can consider as a hole within the polymer, and then because of the triaxial stress, what happens is this hole opens up, and it opens up completely, and then we have very quick fracture of the polymer. This takes place very fast. Okay, and the final thing I'd like to tell you for today is how do we essentially overcome crazing, because what we have during crazing is that we have some cracks that are growing. Okay. And in order to prevent these cracks from growing, what we do commonly is that we incorporate rubber particles within the polymer. So what the rubber particles do is they can absorb the crack growth by initiating many deformation zones and by stabilizing the cracks. And in this case, the polymer is able to elongate more, since the rubber particles are able to absorb the stress. Okay, and we finish today's course with that. I will not continue. There's only this applied formal properties. And then there's viscoelasticity. I'm not going to continue with that on Tuesday when we have our final lecture. I'll provide you with some maybe problems or multiple choice questions to finalize the revisions. And yeah, that's pretty much it. Thank you very much for your attention. Enjoy your weekend and see you for the final class next Tuesday. Okay? Bye, guys.